Hi everyone. I've decided to take some of my linear regression notes from when I taught numerical problem solving a few years back and just use this as an example to bring you up to speed again if you had some struggles with the regression assignment. And then I will use this to go into the data set that we were working with before. So let's say we have a bunch of data points like this, and when we know that the data points themselves are perfect and that the line travels through each one of these, we can call that line interpolation. The thing is about regression is that we may have a situation where the data points aren't perfect. They represent something, some kind of experimental error, or when we collect the information, it isn't perfect. So in this situation here, we're looking at pavement performance versus pavement condition. And you can look at just the data, you can see that it looks like as pavement gets older, the condition gets worse. But what's the relationship between these points? How do we determine that? If we were to do interpolation, we would come up with an equation that connects every single point here. But you can't do that. There's probably 500 points. So what we're going to do instead is come up with a line that represents the best fit of all these data points. But it's a best fit of a certain measure, and that measure is what we call the residuals, or it's essentially we are trying to come up with a line that minimizes the point between each of these points and the line that comes up with best fit. Now, if we were to take all of these data points and just take the average, we end up with some kind of condition line that would just go somewhere between the points like this. But we know that just by looking at this graph, we can tell that as pavement gets older, condition gets worse. So the average doesn't really tell us much. And that's what regression can do. Regression can give us that indication of how well what are the variables that matter and in connection to one another. So as you can see, we got two classes of road here. Both of them have a lot of data points, and we can see some kind of relationship between age and condition. So we know that taking the average condition of all of these roads wouldn't necessarily be useful. The useful component is understanding that there's a connection between age and condition. So the regression line represents the best possible, the best possible solution to the question of minimizing the distance between something that we measure and that line. So we're going to have data points all over the place, and this line represents the line is the minimum distance between these points, between that line and the measurements. And we would call this distance here a residual, or the leftovers. So we get some kind of x value, we get some kind of y value. Now, when we're going to calculate r squared is a ratio. That's basically telling us how good our model is. And it's a ratio of two things. This right here, which is called the total sum of squares. What you see here is you have I minus y bar. So essentially, you're comparing each individual y value to the average and then squaring it. And the reason that we square it is because if you just take one minus the other, overall it'll tend towards 0. And we don't want it to go to 0. That's why we sum the squares. So this is what we call total sum of squares. And see, we've got a total sum of the squares different between each individual y value and the average. Now, our model is the difference between the y value here and what the y value is supposed to on our line, which is this a0 minus a1x. So if our model has, when we put in an x value to whatever equation that we find, it's going to give us a predicted value. So this represents yi minus the distance between this point and our line of best fit, our equation. So that's what we call the residual. Then we square that. So we see we have got all that and we sum them all up. So R squared is the ratio, this value here minus this value here over this value here. So the closer that each of these data points are to the y value originally, the smaller this value is. And the smaller that this value is, the closer to 0 or closer to 1 that this minus this divided by that gives you. So if we were just to take all of the x values and all the y values, you can see we get an average value for them. And that average value doesn't tell you if there's a connection between the points. So what you see here, xi, yi, xi squared, etc., these are all intermediate values that we use to help us find the sum of squares and to come up with the regression line itself. It's the behind-the-scenes calculations. So in here we can have two lines that both have the same slope. We can have the same equation for both, but one has a greater dispersion than the other. So what that can mean for us is that, well, this line down here would have, what do you think, a higher or a lower r squared than this one up here? It would have a lower r squared because the distance between this line and that point squared plus the distance between this line and this point squared, the sum of those squares of the residuals is greater than this one, which would make the r squared of this lower. What that can tell us is that maybe there's some other data that we need to include in here, that maybe this line fits it very well, but there's other things that are outside our control that we weren't able to measure. So when we run our regression line through this whole bunch of points, you can see that we have a y equation up here, right? We have a coefficient, and we have an intercept, and we have an r squared value. So this line here represents the line of best fit. So it minimizes the distance between that line and every single point here. The sum of squares of residuals, it's the best line. Therefore, and then the total sum of squares, which is the distance between each of these points and the average, minus the distance from each of these points to the best fit line, divided by the total sum of squares, gives you that ratio of r squared. So if we start moving into multiple linear regression, and I just had this as an example of what the rainfall intensity impacting something. Can't remember now, so I'll skip it. So here's the things that an equation that impact productivity, for example. So we've got productivity as a function of the type of pour, volume of concrete, number of trucks on the job, weather, cycle time, loads, etc. What we have here are coefficients in front of each variable, and these coefficients we determine through some kind of regression equation. Now, relating to what we've the discussion we had earlier about whether these values make sense, you have to make sure that each of the variables that are in here are unique. There's not two variables counting for one, because like what happens if there is a variable that's, say, number of trucks on the job and number of dump trucks on the job? Well, in that case, that could be in the, you could put that in the model here, but it wouldn't be appropriate to do that, even if the p-value is appropriate, because one's a subset of the other, and there are some tools that can help us better understand that. So what is happening here is essentially when you've got x values, x1, x2, x3, and this would be like x1, x2, x3, so whatever we've got for those values here, all of those can be put into a matrix. And this is what's happening behind the scenes when you do regression. So you don't see this step, but I'm showing it to you so you know that the values in this matrix here are a function of like the x1 values all summed up, x2, x1 times x2, x1 squared, etc. all go into this table. And or into this matrix, and then you have some of the yi values, some xi, yi. So it's a whole bunch of stuff going on here. But the bottom line is that with these values here and these values here, you're solving for coefficients. That's what regression is doing. It's taking all these values, doing the operations that it needs to do in this matrix, same with this, and then you do your matrix operations to solve for the coefficients. So that's what, when you're getting the regression into the Excel, that's what's happening. So if we have this this example of two variables, yi and x1, x2, essentially you have to, again, what's happening behind the scenes, you don't have to do this for your assignment, but what's happening behind the scenes is that the computer is creating a table that needs each of these values in here. So there's an x1 squared, there's an x1 times x2, an x2 squared, x1 times y1. All of these values are being calculated behind the scenes. And then they're being put into a matrix. And after they're being put in the matrix, you then are essentially solving for a0, a1, a2, which are the coefficients of that equation. So a0 is the intercept, 54.3, a1 is the coefficient in front of x1, and a2 is the coefficient in front of x2. Then when we calculate r squared, we are essentially comparing the y value with the overall average squared, and then the y value with what we would have predicted from our model, or what our equation tells us when we put in x1 and x2. We sum up the sum all these values up, the squared values of those, and take the ratio of this minus this divided by that, and that gives us our r squared value. When you plug it into regression into Excel, you can see here's our coefficients that we calculated. There's our r squared value up here. You can't really see it, I guess, because I have this thing in front of it. Let's click to add title. There you go. So you can see we have that, and we have p-values that are less than 5%, which is good, and we have coefficients here. We're just dealing with a couple of coefficients, so and we don't really know what the data are in terms of, I just made it up for this class. But now let's take a look at what this means for, let me just scroll through here. We run through our regression. We did this already in our other class, and we talked about residuals. So now I'm going to bring up our data.